Hello everyone, my name is Bin Guo. I'm a postdoc at the Center of Ocean Energy Research at Maynooth University, Ireland. The topic today is about modeling of a wide-body impact particle mechanism for wave energy conversion. This work is funded by the Marie Curie Action. In this talk, I will introduce the background briefly and then discuss the modeling of the wide-body impact wave energy converter. Numerical results will be discussed in terms of frequency response and the nonlinear dynamics of the system, followed with some remarks. For wave energy converters, one critical subsystem is a particle of devices which generates electricity from motion. In a simple way, the PTL can be modeled as a linear mass spring damper as shown in Figure A. There are some studies show that a properly designed nonlinear PTL can enhance the system performance as shown in Figure B. A snap-through mechanism by two oblique springs can achieve negative spring. In Figure C, if a unidirectional or quadratic PTO damper is used, it is possible to have more power than a linear one. For these hearing point observers, another concern is about end protection. In this study, we focus on the wide-body impact mechanism to see whether we can achieve both performance enhancement and stop protection. As shown in this figure, a floating buoy with mass mb oscillates under the excitation of incident waves, and in the mass mm is connected to the buoy by a supporting spring K1 and the linear damper C. And it oscillates due to the interaction force with the buoy. In practice, a linear generator can be used to replace this damper here. The key mechanism in this system is that there is an upper and lower impact springs attached to the top and floor of the buoy. When the relative displacement exceeds the upper or lower gap G, these two springs can provide impact mechanism to the system. This kind of wide-body impact mechanism can induce rich and complex nonlinear dynamics to the system. So here comes the question, can we make use of this nonlinear phenomenon? Or what's the pros and cons of the system? Can it achieve effective and stop protection? The motion of the buoy is governed by the excitation force due to the incident waves, the radiation force due to the motion of the buoy, and the hydrostatic force due to the mismatch between the gravity and the buoyancy, and the interaction force between the buoy and the inner mass. The radiation force can be written as the Cummings equation, and its convolution term can be approximated by a state space model. Here gives some results of the radiation force approximation. The excitation force can be written as a convolution term of the Kernow function and the wave elevation. Unfortunately, the Kernow function is non-causal, and hence causalization and the wave prediction is required. And after that, we can use a state space model to approximate the excitation force. The motion of the inner mass is quite simple. It's only governed by the interaction force, but the interaction force depends on the relative displacement between the inner mass and the buoy. When the relative displacement is larger than the upper gap, the upper impact spring is active. When it's lower than the lower gap, the lower impact spring is active. When the relative displacement is within these two gaps, only the supporting and spring and the PTO damper are active. The frequency demand response is given here in terms of relative I/O. I/O is the response amplitude operator. In simulation, regular waves are used with wave height of 0.8 meter. The figure shows that the system acts as a bandpass filter. It is expected for a two-body point observer. The relative I/O is small when the wave frequency is lower than the natural frequency. This shows a high survivability in actual sea states as the actual waves are of low frequency. Comparing the results without impact and with impact, the natural frequency is increased and the bandwidth was extended by the vibro impact mechanism. Another very interesting phenomenon here is the multi-stability. When the frequency increases, we can see the Lucas is from A to B, C, D, E, F. But when the frequency decreases, the Lucas is F, E, C, B, A. So between the points C and E, there exists multi-stability. Another concern is about the end-stop protection. When there is no impact, we can see the physical constraint is violated. And when we add the impact in, but if the impact stiffness is too small, we cannot constrain it effectively. The way that we can increase the stiffness of the impact springs to limit the physical constraints. The gap G is one of the most critical parameters as it can directly influence the impact occurrence. Hence, here we use G as an example to show the bifurcation analysis. In figure A, G is varied in a wide range and it can be divided into 8 zones. In the zones 1, 3, 6, and 8, the dynamics are simple. Typical trend chases for in zone 6 is shown here, and we can see the dynamics are simple and periodical. In zones 2 and 4, the motion is chaotic. Typical time chases shown here that the motion looks a bit irregular, even though the incident waves are regular. In the zones 5 and 7, we can see there exists multiple solutions on multiple orbits. For the very value at here, there exists 3 possibilities and shows here. As G increases or decreases, some typical bifurcations can be observed. For instance, at this very critical point, what we observe is a gradient bifurcation, and also period halving can be observed here and here. The system performance are evaluated in terms of relative I/O, average power, peak to average power ratio. As the system dynamics varies, we can see the performance indices varies as well. And for practical problem, we can see that this bifurcation analysis can give us some guide to select a good design parameters. For instance, the gap values in zone 6 is preferred as first, the dynamics are simple. Second, the relative I/O is large, but still within the physical constraints. And then the average power is high and the peak to average ratio are small. And another very interesting is about zone 7. There exists two orbits. The one with impact means high power, while the other one without any impact means low power. If there exists some control methods to switch the orbit from one to another, this will give us a possibility to tune or detune the system. When multi-stability exists, the system dynamics depend heavily on initial conditions, and the basin of attraction is a useful tool to investigate how the initial conditions influence the system dynamics. In this figure, an attractor is a Poincare section point representing long-term behavior of the system dynamics, generally, which is an orbit or solution of the system. The basin is a set of initial conditions with which the system dynamics converge to this attractor. In this figure, the initial conditions in the green area lead to attractor 1, which is unstable but indicates high power. The initial conditions in the blue area leads to the attractor 2, which is stable but means low power. As we can see from figure B, we can make a comparison between the excitation force and the PTO force with or without impact. When we compare the PTO force with and without impact, we can see that when impact happens, the magnitude of the PTO force is enlarged, and the phase shift between the PTO force and excitation force are reduced. This is why we get more power for this one. To conclude this study, the Weibull impact wave energy converter has bandpass characteristics, and its response is very low in extra waves of low frequency. With proper design, the Weibull impact mechanism can enhance the power capture and enlarge its bandwidth, at the same time provide effective and stop function. The drawbacks are that the Weibull impact mechanism can also increases the peak to average power ratio and induces rich and complex nonlinear dynamics to the system. To overcome these two drawbacks, the potential solutions are we can use parametric study or bifurcation analysis to optimize the system design, or using control methods to switch between possible orbits to tune or detune the system dynamics. At the end of this talk, we are pleased to show you that we have a special issue in the journal IET Renewable Power Generation. The topics are given here, but not limited to these topics, including the modeling and control of Viwec system, fluid dynamics, and testing modeling of PTO systems, and tank testing and model verification. The other studies are also welcome, such as the multi-function offshore plentiful, energy storage and grid integration, and the power resource assessment. The submission deadline is the 1st of December. We have several months to go. Special thanks are given to the European Union H2020 framework, and the study is funded by the Marie Curie Action. Thanks very much for your attention. If you have any question or inquiries about the paper or related to the special issue, please feel free to email us.